There's an applet for the Doppler effect. This flash animation shows a moving source emitting circular waves. It gives a source frequency of 2. Let's assume that it is 2 hertz. All these numbers are actually dimensionless, but let's just say that that one is 2 hertz. The slider on the left controls the ratio of speed of source to the speed of wave. Okay, the slider is on the right hand side, and here's this ratio 1.46. We could change that. I'm just going to leave it here at what I just have 1.46 if I get that back. Okay, 1.44 referred to as the Mach number, and it's pronounced Mach because he was Austrian. And that means right now that the source here is traveling faster than the velocity of the wave, and so you get that kind of shock wave. Or if this is sound, which we hear now, you get supersonic sound. Oh, I'm sorry, the source is at supersonic. Okay, here we get 0.82 as the detected frequency. I'm going to jot that down for our calculation later on. The cool thing about this one here is that you kind of hear not only that the frequency is lower, but you also hear that the sound diminishes the further you're away from it. Of course, if you're ahead of it, the sound didn't have time to actually get to you because it's supersonic right now. I'm going to quit this one here, and I'm going to slide it down here to about this value here, yeah, 0.52. And now the source is slower than what the wave is, so it is ahead of it, and we can see over here that we get a detected frequency of 4.15, and when the source is moving away we get a detected frequency of 1.32. Again, I'm going to jot these down so we can do a calculation with that. And of course I encourage you to use this applet here and play around with it. So, Doppler effect. Still trying to figure out how my pen and my tablet are working, and there was no reason for me to write in red, but I just did. So the source is approaching was the first one, and maybe some of these here I should just type, and that was supposed to be a U. So the source approaching, and the way we look up the equation in the book, when the source is moving toward a stationary observer, then the observed frequency equals the source frequency times 1 times fraction bar 1 divided by 1 minus the source velocity divided by the velocity of the wave. And you may want to pay attention, they often use sound as the wave in physics books. In our particular physics book they use the subscript S for the source, not for sound. The actually sound velocity is this one right here, and again this one is the source velocity. So when I plug in numbers, so that means we have 2 respectively, I call it 2 hertz, times, as it's approaching, 1 divided by 1 minus, and then here for Vs over V they already gave it to us as a ratio 0.52, so no matter what the velocity of the wave is, the ratio of these two source velocity over wave velocity is 0.52. So for example, if we actually do have sound, as we heard there, 330 meters per second roughly, then the source velocity would be roughly 165 meters per second. But they already gave it to us as a ratio. And then I plug in these numbers, and when I do that on my calculator, I come up with 4.17, and that is perhaps hertz. And you saw in the video or the applet that it was 4.15 measured. So that's right on. I mean, within measurement errors, and of course this is only two significant figures, so actually it should be 4.2 hertz. And the other one is, if I'm able to just copy this one here, I don't have to rewrite the whole thing. Let's see if this works. Yep, there we go. Hopefully, yeah, there we go. Saves me some writing. So when the source is receding, then the equation changes, but not a whole lot. Just right here, there's a plus. And then I plug in the numbers. And that was 2 hertz times 1 divided by 1 minus plus 0.52. When I put that into my calculator, I come up with 1.32. Respectively rounded, it should be 1.3, of course, two significant figures, and that's exactly what they showed us in that applet, 1.32 hertz. So that one is right on. And of course we saw that too, that as it's approaching, the frequency increases that we observe, and as it's receding, the frequency decreases. And then the first one that I had, the one with the supersonic speed, that one I had these numbers, 2 hertz times 1 over 1 plus, and that one was 1.44, the ratio. So if this was sound, then the sound wave would go at 330 meters per second, and the source, the airplane perhaps, the fighter jet, would go at 1.44 times that much, which is, top of my head, about 470 meters per second. Actually, I have the calculator right here. Yeah, 475 meters per second. Which would be roughly 1,000 miles an hour. As far as plugging in that one was also only the source is receding, because with this supersonic airplane we just didn't get any sound standing in front of it because it was faster than the sound. So when I plug in the numbers for that receding, I get 2 hertz times 1 over 1 plus 1.44, and I come up with 0.820 hertz. And if you recall, the applet showed us indeed that it was 0.82 hertz. And here's a video on YouTube for the Doppler effect. Respectively, you can just search for it yourself. The quality might be actually better if you do it yourself rather than in this recording. So here we go. And of course, the loudness is going down as it recedes, but try to listen to the pitch. The frequency, the pitch is higher as the ambulance approaches, and it's lower as it recedes. This is hyperphysics. I'm going to go to sound and hearing, and then the Doppler effect. And here you find the same equations as you find in any textbook, with the source approaching or receding, and perhaps even the observer receding or approaching is on here. Here is a calculation that's automatically putting into these equations here. So let's assume we have a temperature of 20 degrees Celsius. So what I mentioned earlier, 330 meters per second is actually around 0 degrees Celsius. But we'll just use this one here. If the source frequency is 2 hertz, and then the velocity of the source, well, there I would have to calculate. If I take 0.52 of 343.7 meters per second, then my source velocity is 179 rounded, and it calculates in miles per hour for me. 400 miles per hour, wow. And of course, this is what we calculated, and this is what we measured, 4.17 for the approaching source, and then we had 1.31 for the receding source. So we had those numbers, and then the other one was for the supersonic one, where I take this one here times 1.44. So basically the calculations that I do here are confirming what we did earlier. While earlier we just used that ratio that was given, here I'm actually giving it real numbers for the speed of sound, but either way worked if the problem only asks for the ratio. So just 4.9, so 495, and there is again 1,100 miles per hour. And this one here, that's why we also had 0.82 hertz. This one here, yeah, that just doesn't quite work. There are no negative frequencies. You saw that on the screen earlier as well.